Alright, welcome back. In the last video, we saw the remarkable idea that you could consider an aperiodic signal as a signal that repeats whose period is infinity. Really, it does not repeat. But we're saying, okay, let's consider a signal that does not repeat as one that does repeat, but you just haven't waited long enough to see it actually repeat, i.e. its period is infinity. So let's continue on with this idea, and in this video we're going to formalize the construction of the continuous time Fourier transform, that is, be able to find the CTFT for any signal, not just the square wave that we did in the previous video. So again, I have, just like the last video, I've got two signals that are related. One is periodic, and I'm calling that one x sub t of t, and it's got a period capital T, and the other one is not periodic, and I'm calling that x of t, and they're related being that one period of this guy is the same as this signal here. Okay, and so it's x of t that we ultimately want to analyze. So let's start with what we can do. We can analyze the frequency content of the periodic signal using Fourier series. So we can use the synthesis equation and say that k is we're gonna sum over k goes from minus infinity to infinity of its Fourier series coefficients times e to the j k omega 0 t, and then I'll just remind you that omega 0 is 2 pi over t. Okay, and then remember that the Fourier series coefficients, right, if we had a mathematical equation or something that we would use to model one of these little squiggles, we would find its Fourier series coefficients with the analysis equation. We could go over one full period, right, xt of t e to the minus j k omega 0 t dt. That would get us the Fourier series coefficients. And so that's the Fourier series representation of xt of t. Now, because in this range of integration, negative t over 2, maybe here, to t over 2, x of t is the same as xt of t, we can actually be a little crafty, and we can write this from minus t over 2 to t over 2 of x of t. Because again, in that range, both signals are identical. So I might as well just do that because it's x of t that I want to analyze. I don't want to be stuck analyzing periodic signals. Now, outside of this range, x of t is 0. So I might as well not start at negative t over 2 because we don't want something that's related to the period of this thing. Let me just go from minus infinity again, because this is all 0 over here, so I might as well just begin at negative infinity and go to positive infinity. That way I have something close, or almost, that's independent of t, capital T. Now if I take this and I multiply both sides by t, then I have something that is independent of the period and the frequency. If I write this power, if I consider k omega 0 as being a continuous variable omega, and then sampled, all of this sampled at omega equals k omega 0. So we're drawing upon something that we did in the previous video. And if you remember from the previous video, then it's this thing that we called the envelope. And we said that the envelope is saying something about the frequency content of x of t. And it's that thing, we're going to call that capital X of j omega. That's the Fourier transform of x of t. So you may have been introduced to the Fourier transform in math class in differential equations, and you saw the Fourier transform as being, something mathy that is useful for solving differential equations. Actually, it's much more applicable than that, much more powerful, and it tells us the frequency content of this signal. So we take x of t and we compute this integral, and then we get this capital X, and again, that's the Fourier transform, and we're going to call this equation the analysis equation. So it will be obvious, we've covered many equations that are called the analysis equation. It'll be obvious which one we're referring to. This is the analysis equation. Give me x of t, I will analyze it to find out its frequency content. Okay, now let's see if we can synthesize x of t. If given capital X, the frequency content, can we get back x of t? Okay, so remember that the Fourier series coefficients are 1 over t x of j k omega 0, right? The Fourier series coefficients of xt, the periodic signal, right? Take capital X, divide it by t, right? Get the t to the other side, and then sample. Plug in omega equals k omega 0, and you've got the Fourier series coefficients. Now with the Fourier series coefficients, you can synthesize back the periodic signal using the synthesis equation. So I plug in the Fourier series coefficients, so they're 1 over t x j k omega 0, right? Then e to the j k omega 0 t, like this. And remember that t is 2 pi over omega. So I'll bring 2 pi over omega 0. So I'll bring out the 1 over 2 pi there, and we'll write this as x j k omega 0 e to the j k omega 0 t, and then I need an omega 0, right? Because t was 2 pi over omega, so 1 over t is omega 0 over 2 pi. Okay, now I need some space, so I'm going to delete this. I'm going to try to keep our result, though, so I'm going to keep that up there. Now, let us look at this part here, x times e. So everything but the omega 0. And let's consider k omega 0 as being a continuous variable that's being sampled at this k omega 0. So in other words, I want to consider x of j omega times e to the j omega t, okay, where omega is a continuous variable. Now, without knowing what our signal is, and we have no idea what this looks like. I mean, we're keeping this general. That's the idea. But I'm going to draw something, anything, just to get a good visual of what we're dealing with. So again, I'm just going to draw something for the sake of argument. Maybe this thing looks like this. Okay, and so that's this plot. And I'll give it an axis. Maybe here. Okay, and this is omega. This is a function of omega. Okay, so the idea again is that we're sampling. So we plug in the kth harmonic, and so that would be maybe the 0th harmonic. So we have this thing that we sampled from, and so we have this height, right? So this function x times e is telling us this height, and then we plug in, the k equals 1. So this would be the first harmonic would be omega 0, and then we plug in the second harmonic, 2 omega 0, and the third harmonic, and we do this forever, right? That's what we're saying here. We have a sum of this thing at k omega 0. Okay, so that gives us the height at these equally spaced points. And then then we multiply that by omega 0. So if we take the height of this thing, the k equals 0th harmonic, and we multiply it by omega 0, omega 0 is the width. So you can look at that as getting the area of that thing. And then when k equals 1, that's this height, multiplied by the width, that's the area of this thing. And then the area of this thing. And the area of this thing. And since k goes from minus infinity to infinity, we also have all of these areas as well, right? Okay, so what we're saying here is that this sum is kind of calculating, we have a sum of all of these rectangles, or the areas of all these rectangles. And remember we said that the genius of Fourier's work was to say that this guy, the aperiodic signal, has a period of t equals infinity. And so what happens to the spacing of these rectangles as t goes to infinity? Right? Well, that spacing goes to 0. So what happens to a sum like this when the spacing goes to 0? That's called a Riemann sum. And you should have learned it in calculus when you were studying integrals. When those rectangles' widths go to 0, this passes as an integral. So now, here's where the magic happens. If I take the limit of this equation as t goes to infinity, x sub t approaches x of t. So on the left of that equation, I have x of t. And then on the right of that equation, I have 1 over 2 pi times an integral from minus infinity to infinity of x of j omega e to the j omega t, and then omega 0 becomes d omega, a small change in omega, and that's amazing. An application to Riemann sum, who would have thought? Anyway, that's called the synthesis equation. We're going to refer to that as the synthesis equation, or the inverse Fourier transform. So this is the Fourier transform, and this is the inverse Fourier transform. Okay, the fact that an inverse even exists is amazing. That means that you can describe any process in time. You throw a ball up and you plot its motion in time, or you can alternatively and equally express it as its frequencies, because there's an inverse, so you can always get it back. You've lost no information about the process. There's an inverse transform. That's amazing. So we have this analysis equation, we have the synthesis equation. Now, coming up then, of course, we want to practice these things. How can we, given a certain signal in time, how can we use the analysis equation to find the Fourier transform? And let's try to work on our intuition to see, exactly what the Fourier transform is telling us. So I've got some example videos coming up.